All right. Hello, everyone. In this talk, we'll give you an overview of OCP NIC 3.0 manageability features. I'm Hamel, and I'm jointly presenting this talk with my colleagues, Patrick and Bob. So for the agenda, we will provide motivation for OCP NIC 3.0 standards-based manageability features. Then we'll discuss the interfaces and transport, and then go into more specific feature details. So to begin with, as a successor of OCP MAS 2.0 specification, there were a number of enhancements that went into OCP NIC 3.0 specification. One of the key area that we focused on was standards-based manageability. And that is the main topic here, and we'll cover these features in the next few slides. So OCP NIC 3.0 specification, standardized management traffic communication over DMTF defined standard transports. And DMTF has RMII based transport that is used by NCSI specification, as well as it has management component transport protocol MCTP specification that is used over multiple medium SM bus or PCI VDM. So this basically defines for OCP NIC 3.0, the communication for management is based on this standard transport, and you have three possible implementations of that. Either you implement RBT or MCTP, or you support both. Now we'll get into more specific feature level detail. One of the first one is OCP NIC 3.0 defines a standard way to do BMC MAC address provisioning. And this is important for an implementation where BMC is sharing the NIC with host. In this case, BMC requires to use the MAC addresses that are provisioned by the NIC. In this use cases, what OCP NIC 3.0 spec standardizes the standard way to do this provisioning scheme, as well as the provisioning formula, which works across single host, multiple host, and multiple network port partition environments. And those are all defined in the spec. So now I'm going to turn over to Patrick to cover next two features.
Thanks, Hamel. Some additional features of OCP NIC 3.0 involve temperature and power reporting. Now, obtaining the NIC temperature and power reporting will help improve your systems management overall. And the specification which helps define this capability is based on PLDM, and that'll give sensor-based definitions for both temperature and power capability. The temp reporting is available for high TDP devices and is supported in multiple power states in S5 and S0, so either at aux power or full power. The reporting accuracy is available up to plus or minus 3 degrees Celsius. And in addition to the temperature, power reporting for estimating your board or runtime power can be provided. Components such as your pluggable transceiver module, if they can support power and thermal sensing, that can also be provided in OCP NIC 3.0. Lastly, there is an optional self-shutdown feature. The NIC is designed to self-protect if it's capable to detect its own temperature and protect itself from high operating temperatures. Now, all of this reporting through PLDM could be done with asynchronous event notification or through polling-based methods such as a get sensor reading, which could accumulate the sensor data and take that into systems management reporting. The next feature we'll talk about is about firmware inventory and updates. An OCP NIC 3.0 adapter can have multiple firmware components. They may be applicable to the data path, control path, or management path operations. The OCP NIC 3.0 spec defines firmware inventory and update capability, and that firmware inventory includes the capability to retrieve the version information, device model, and device ID details. It's desirable that OCP NIC 3.0 implementations support an OS-independent mechanism for the manageability of firmware update. The firmware inventory and update is based on another PLDM specification known as PLDM for Firmware Update Spec. That specification does provide full capability to provide an inventory-only based method or an inventory and an update-based method. For more features of OCP NIC 3.0, I'm going to turn it over to Bob to continue forward in this presentation.
Thank you, Patrick. So the network controller sideband interface is a long-established DMTF specification that defines really 3 different communication paths between the NIC and the BMC. The first is pass-through data, which allows the NIC to be a pipe between the network interface and the BMC, allowing the BMC to appear on the network for normal network traffic. NCSI also defines commands and responses to handle control, inventory, and monitoring features of the NIC that the BMC would like to control. And lastly, there are asynchronous event notifications defined, where if some event happens on the NIC, it can notify the BMC of these events without having the BMC need to poll for them. NCSI is defined as operating over 2 different paths. One is the original RBT interface, which is a RMII-based concept where it's been extended to support a multi-drop feature. Multi-drop requires the addition of hardware arbitration to pass tokens between up to 4 different OCP 3 NIC adapters, allowing each one of them to talk in sequence. RBT, being RMII based, is essentially Ethernet, therefore the framing of NCSI is Ethernet in nature. MCTP is a transport protocol that can operate over several different physical interfaces. The main ones that are focused on are SM bus and PCI VDM that's useful for higher speed communication. The NCSI spec defines package addressing and the resulting hardware arbitration scheme that is used for RBT. The OCP NIC 3.0 spec defines both SM bus interfaces as well as RBT interfaces on the primary connector, so that the BMC has its choice of which one to use in communication, with the NIC controller that's on the OCP3 NIC card. Also, the OCP spec defines timing and routing parameters to assist the implementation of NCSI on both the OCP NIC 3.0 card as well as the baseboard itself. So now I'd like to talk about the FRU that's on OCP NIC 3.0 cards. So the OCP spec defines a common FRU format and content requirements. These are based on the existing IPMI FRU specification, and OCP has, in addition to what's defined in the IPMI spec, its own OCP OEM record to handle things that were not defined by IPMI. The FRU is readable in all power states, both ID mode, programming mode, aux power mode, and main power mode, which would allow the BMC to make a decision as to whether or not it's appropriate to power up the OCP NIC 3.0 card given the current system configuration. There's an optional mechanism for FRU write protection to give an additional layer of protection against modification of the FRU content when it's plugged into a system. And lastly, the FRU content includes things such as the manufacturer name, power, thermal tier requirements, cooling and airflow that's required based on the card's design. There are breadcrumbs for manageability schemes that are supported, as well as a device ID. And so now I'd like to pass it back to Hemel to talk about the software stacks that are involved in making this all happen.
Thanks, Bob and Patrick. So as we discussed in the talk, we started with standards-based interfaces and transport, and we talked about specific standard manageability features in the OCP NIC 3.0 spec, including temperature power reporting, firmware inventory update, NCSI communication, and then standardized FRU content. So this is how it all fits together from a software stack standpoint. It builds on the physical layers that we talked about, including RMII, PCI, VDM, and SM bus. And then you have standard transport, RMII-based transport, or MCTP, which can go over a number of physical medium here. And all these features that we talked about are supported through the upper layers where NCSI commands or through PLDM communication, those implementations can be realized. So this is how it all fits together. So with that, I would like to summarize that we talked about system management of OCP NIC 3.0, how important it is, and standards-based manageability is critical to that. And that's what we discussed in this talk. So thanks everyone for listening. With that, we'll take question and answers.
Okay, thanks everyone. At this point, we'll go over the questions on the chat and as well as in the queue. So the first question on the chat was, which interface is the temp information retrievable from? So temp information in OCP NIC 3.0 is PLDM based. So PLDM communication can be over any transport, RBT or MCTP. Hence, the temp information is retrievable over any of the interface on which you have PLDM support. Second question was about, does monitoring of OCP NIC temperature using PLDM supported while card is not powered up in aux power? The short answer to that is, with out-of-band management, the PLDM based temp monitoring is available in aux power state. It also depends on the communication medium. With PCI VDM, generally communication is available only in S0, while PLDM or RBT or PLDM or MCTP SM communication is available in S5 and S0. After that, there was another question on how about UFI support. Currently, UFI support is not defined in the OCP NIC 3.0 spec. One more question here, do we have any software driver available for supporting PLDM and MCTP in open source? For that one, I'll point you to look at OpenBMC. Let me go to Q&A. So there was a question on, can you discuss NCSI or RMII for a NIC with 2 ports? The NCSI spec supports NIC with multiple ports. So from spec standpoint, that's supported. There's one more question here. Is it possible, according to OCP 3.0 spec, to have multiple BMCs in different medium but which manage the same NIC. So OCP NIC 3.0 spec is silent on multiple BMC. Currently support expects typically single BMC managing the NIC. Another question here is, should OCP NIC 3 be able to work simultaneously in both SMBus and PCI VDM? The way the spec is defined, multiple sideband interfaces can be active at the same time. So with that, I'll wrap up. Bob or Patrick, do you guys have anything to add?
No, thank you for everyone for attending, and hope your questions were answered by Hemel and that you enjoyed this.
Okay, thanks everyone.